Part 3 of our lecture. Here I will give you a brief descriptions how this method is being used. This method is still very useful method, very powerful method, and still being used in a lot of companies. Here we will look first. We need to remember of our total cost formula. Total cost formula, if you still remember, summation of dj over qj plus times with c naught plus summation of I cj qj over 2 plus with the constraint. This is our total cost formula. And now let's say we have a constraint or restrictions of summation of dj over qj. If you still remember, this is the number of order, and now we have constraints inequality of n. It means our number of order for each item will be reduced at the certain restrictions of n. Here I represent everything in symbol, where we are going to do on experiment or practical application, we will get it easier. Okay, so if we look here, we have our qj here as a denominator, and here is a linear, plus here is a still denominator. So we call this one as nonlinear optimization problem. In order to solve the nonlinear optimization problem, one of the powerful methods that we can use is the Lagrangian expressions. So in the Lagrangian expressions, it says that all the inequality need to convert first for the equals constraints. Okay, why? Because we will have our feasible solutions, which when we have our total cost, and this is our optimal quantity, but now this is for one item. When we have more than one item and we have constraints of n, it means that basically it will not at this Q optimal, but going beyond on that, it means the increase in terms of the quantity. And if you look here, this is our line, and this is less than or equals to of the constraints given. So it means that we need to change this inequality which binding with our constraint optimization problem, so that we can change these equations or inequality towards summation of dj of qj is equals to n, where we can substitute this equation, the whole equation, into our total cost to make as Lagrangian expressions, where summation of dj over qj minus n equals to 0. Okay, or minus n. Okay, so what the next thing we should do is we need to make sure our new Lagrangian expression will be Lagrangians with q and lambda, because here I'm still using of lambda, where summation I'm still using the same formula. Let me take another marker. Same formula where okay, where dj over qj c naught plus summation of I cj qj over 2 plus lambda. That's what we have here, lambda. Lambda, we take all the equation from the inequality that we convert to equality because of the feasible solutions. So here we get dj over qj minus n. Now I hope you understand. For every restriction, the same method or procedure is being applied. So let's say now you have a different in the budget or different the average inventory. You need to make sure the formula here should be the different one, and you need to convert into equality and put it back as a Lagrangian multiplier. And do remember, if you want to find the optimal quantity, we do the same thing, where we use the first derivative of differentiate the whole equation towards the q, where when you convert it, you will get summation of negative dj over qj squared c naught plus I cj means summation over 2 and plus with alpha d j over negative qj squared. And from here we can rearrange. You can look on my slides where we can get our q optimal of j equals to square root 2 d dj. In the bracket we will have lambda plus c naught over I C J. If you look here in our QJ here, although we managed to get QJ is good, but here we still have our lambda. We need to determine the value of lambda. So after we determine the value of lambda, it will be easier for us to calculate using our new EOQ. How to find the lambda value is easy. Since we still using the same formula where we differentiate now dl towards d lambda, where we will get d lambda is equals to d j over q j minus n, and when we make it as a 0, it means that we get back dj over qj equals to n. So what we should do next, we already know our dj and qj. It means that we can convert this one. So we use dj over our qj, we take back our this one, square root of 2 dj lambda plus c naught over icj equals to n. And the final equation that we'll get of lambda is where you can see the derivation, or you can do yourself the derivation, and when you calculate here, you will get I over 2n square summation of djcj square minus c naught. This is the value of lambda. It means you already know you have the value of n, you already have value of dj, cj and c naught. Now you just need to substitute the value of lambda, and after you get the value of lambda, you can substitute back into the qj, so that you now can determine what is your optimal q and number of order. So the same formula applied. So in here, if you want to solve any methods in multi-items, you only have 3 steps. The step 1 is finding the equality, the inequality. After that, you need to change into the feasible solutions and make it to as an equal. Second, you need to find our qj optimal. Before you find the qj optimal, definitely you need to find first the lambda value. After you get the value, you can start to put in the value in your qj, and you can find the modified EOQ. And actually you can solve this one not only for one item but all the items, and this is how the software start to come into the picture, because it's very difficult if you want to solve one by one. Maybe if 1 to 10 items is still okay, but how if you have thousands of items? So then the SAPs, it means the SAPs and Oracle software came into the picture. Thank you.